Hello, today I will discuss Eisenstein Criteria for polynomials. This tells us that if we are given integer coefficient polynomial, p of x, they are a1, an-1, and a0, all of them are integers. And we also know that there exists a prime number p such that p divides ak for k less between 0 and n-1, and an is not divisible by p, and a0 also is not multiple of p square, then we can say that this polynomial will be irreducible. And what does irreducibility means is that p times x can't be represented as rx times q of x. Both of these polynomials are non-constant, and they have also integer coefficients. Their coefficient must be also from z. Now let's imagine that contradiction of this is that there may exist rx such that x has some coefficients like bk to the xk, then all the way up to b0, and q of x must have coefficients cn minus k times x to the n minus k, all the way up to c0. Here bi must be in z, and also cj will be in z. If we take the product of rx times q of x, what can be seen about the free variable who doesn't have any x? a0 clearly must be equal b0 times c0. And we know that a0 is divisible by p, but not p square. So this means that exactly one of the b0 or c0 must be multiple of p. And with all laws of generality, we can assume that b0 is divisible by p, and c0 in this case can't be divisible by p. Otherwise, we will get that a0 is divisible by p square. Now look at the coefficient of x. How can we get the coefficient of x? If we take rx times q of x, now we will have bk to the x to the k, all the way up to b0, times cn minus k times x to the n minus k, all the way up to c0. Coefficient of x will be c0 times b1 plus b0 times c1, and this must be equal a1. Because we know that a1 was divisible by p, and also b0 is divisible by p, we can assume that b1 must be also divisible by p. b1 is divisible by p because we know that c0 is not multiple of p. Now we know that b0 and b1 are multiple of p. Similarly, we can show that b2 will be multiple of p, because if we consider the coefficient of x square, we will get that c0 times b2 plus c1 times b1 plus b0 times c2 equals a2. a2 was multiple of p, b0 is also multiple of p, b1 is also multiple of p, and we also know that c0 is not multiple of p, so we can conclude that b2 must be also multiple of p, and this is divisible by p. Similarly, by using this logic, we can see that for every coefficient of b, this number must be multiple of p. And now check this. c0 times bi plus c1 times bi minus 1, all the way up to b0 times ci. This equals ai, and clearly this number is multiple of p. Now we can use induction on I, and if we know that all these bi's are multiple of p, and ai is also multiple of p, we can conclude that bi will be also multiple of p. Here I have used the fact that either Q or R has degree more than 1. Otherwise, we may get the number A of n. A of n must be greater of degree of n must be greater or equal degree of p and q, both of these q and r, both of these polynomials. So in this case we don't have an in our case, but we have concluded that all the coefficients of Rx was bk to the xk all the way up to b0, and all of its coefficients was multiple of p. Pi was divisible by p, and clearly this means that an must be also divisible by p. And this is contradiction to our statement that an was not divisible by p. So our assumption that p can be factored was mistake. So we will see that this polynomial will be irreducible. So this was all we wanted to show. If you want to discuss some theorems, please write in the comments, and don't forget to like and subscribe my videos.